Welcome to Data Mining, Lecture 6, Part 1. For this whole lecture, we will talk about text mining. So far, we have already covered association rule mining for transactional databases, classification rule mining, particularly ID3 and C4.5 algorithms for decision tree induction, clustering algorithms, and we have seen two different types of clustering algorithms, namely the partitioning-based algorithm and the hierarchical clustering algorithm. Now we will focus on another subject, which is text mining. There are three parts for text mining. Part 1 concentrates on review of text retrieval or information retrieval, which is a big area which has been researched and developed for almost 30 or 40 years. So part 1 is to review the most important concepts and techniques in information retrieval. And then part 2 and part 3 will talk about new topics in text mining, and you will see some differences between text mining and text retrieval, and you will also see some similarities between text mining and text retrieval. Text databases are large collections of documents from various sources: news articles, research papers, books, digital libraries, email messages, web pages, library databases, and so on. Much of the data are stored in semi-structured format in the following sense. If you look at, for example, email messages, each email messages has some attributes such as sender, receiver, subject, organizations, and so on. Each email message also contains some unstructured data, such as what you put in the email body, which is written in natural language, for example, English. So an email message is a semi-structured data because it contains some attributes and also it contains some unstructured text in the email body. In general, we can divide data into three groups: structured data, semi-structured data, and unstructured data. Structured data refer to those, most notably, relational tuples. In a relational table, which is a structured data type, for each tuple, you have attributes, for example, name, address, gender, and so on. So that's a structured data type in the sense that for each tuple, you have attributes and you specify values for attributes. For example, address is a character string of 50 characters. Name is a character string of 10 characters, and so on. So that's structured. An email message, on the other hand, is a semi-structured data type because it has some attributes and it also has some natural language descriptions. What is unstructured data? You look at this, for example, the body of an article. That author describes events or news using English, using natural language. So that's unstructured data. You look at a web page. A web page is also semi-structured in the following sense. Look at the HTML page, for example. You have H1, H2, H3. You have headers. In some sense, they are attributes, meaning that you want to emphasize certain things using H1, using boldface, and so on. But then you also have descriptions, right? A paragraph for describing something. That paragraph is unstructured. So if you look at the entire HTML page, it's semi-structured because it has some attributes like H1, H2, H3. It also has English descriptions. Okay? One important thing for today's digital library, for example, web, is that the data there, or the database there, is huge. Look at the World Wide Web. That database is extremely huge. So traditional information retrieval techniques become inadequate for the increasingly large databases. Many IR techniques have scalable problems. They work well for smaller data sets, but when data sets become large, the techniques cannot scale very well. So new techniques have to be developed to deal with this situation. So information retrieval, or the shorthand IR, is a field developed in parallel with database systems. For those of you who know ACM organization, you see that there's an ACM SIGAMO special interest group which runs the SIGAMO conference. You also see that they have a ACM SIGA-IR research special interest group which runs information retrieval conference. So these two groups are separate, and in fact, people there are separate as well. Okay, DBMS has a group of people, IR has another group of people. Recently, ACM established another special interest group, which is SIGA-KDD, Knowledge Discovery and Data Mining Group, and this is another separate group. So there are three groups. All of them are dealing with data retrieval, data management, data mining, and data and information. In IR, information is organized into a large number of documents. So what IR people do is to manage documents, okay? And for example, this lecture notes is a document, okay? Information retrieval problem is locating relevant documents based on user input, such as keywords or example documents. So what they have is that they ask the user to enter a query, which is expressed as a keyword or as a combination of keywords, okay? And then the system will find documents that contain these keywords and then present to the user. So a typical example is a library retrieval system where you go there, you type in some keywords, the system will find the documents and tell you which documents has which keywords and so on. But why IR is suddenly now becoming hot right now? Because today we have a digital library and we have a lot of search engines, most famous one being, for example, Google search engines. And they use a lot of IR techniques to improve the underlying search, to give the users most relevant web pages. And they borrow a lot of IR techniques. Perhaps they borrow more IR techniques than DBMS techniques, although they put the data in a DBMS, so they count on DBMS as well, a big Oracle engine. But then on the top, when they present users with solutions to a query, basically that's an IR interface, right? They present a lot of search results relevant to your query. You can try the Google, www.google.com, which is my favorite search engine. I did search almost every day. So I type in a keyword, I can see a lot of results pop up. And this is typical IR search. Nothing to do with SQL and so on. Underlying that, you know, in a backend, you still need a DBMS to support this whole engine, but that's hidden to the user. What the user sees is an IR interface, a query interface, which is similar to an IR system. The user doesn't see SQL anymore on the Google search engine. There have been efforts from DBMS researchers who try to develop an SQL-like query language and put that on top of web. But the efforts, most of these efforts failed. Why? Because they finally observed that the web, the digital library, is not a DBMS. And therefore, if you put SQL, you just create a lot of inconvenience to the user. And once the user doesn't like this, the whole idea fails. They try to put the SQL interface so that you can type in SQL languages on the web, and then the web search engine will search and then find solutions and display to you. Okay, we will talk about some of these approaches as we go further. But many of these ideas just are not commercialized, because they create a lot of inflexibility or inconvenience. And users don't like this. Users still favor Google.com or Yahoo search engine, where you have a simple search window. You just type in some simple keywords and you find the solutions. That's what they favor. So unfortunately, DBMS query languages cannot be transformed to the web query languages directly. There are efforts, there are papers talking about that. We would describe some of these papers later on. So now you see the difference between IR retrieval and the DBMS retrieval. For DBMS retrieval, you type in an SQL statement, and you have to precisely specify the values for each attribute. Select from where. Okay, student name is Robert, degree is BS. You have to specify these attribute values precisely in an SQL statement. And you follow the SQL construct. And they do the exact retrieval, exact match. They find all these matching tuples contain these attribute values and present to the user. That's SQL. On the other hand, for IR, they do approximate retrieval in the sense that user type in some keywords. They find the documents, they present to the user, and they rank the documents so that most relevant documents are presented first. And then they are the second most relevant, third most relevant. If you look at the Google search engine, you see that they always present you the most relevant document, second most, and so on. And they can give you a lot of relevant documents. They usually give you like a 10. You go to first page, then you can keep on looking at the second page of search results, third page, next, and so on. What they do is they rank the most relevant search results first, okay, and they present that result. So there's a difference between DBMS retrieval and IR retrieval. Now you see the difference. IR retrieval is try to get approximate solutions, relevant results, and then rank those relevant results. DBMS to do the exact retrieval, and they don't rank the results. Use the DBMS, use Oracle, you type in the attribute values, and the search engine just gives you tuples containing those attribute values. There's no ranking for search results. So that's a significant difference between DBMS retrieval and IR retrieval. So typical IR systems include online library catalogs or online library retrieval systems. Now, of course, today you see more advanced IR systems, including web search engines like Google.com or Yahoo.com. Those are new generations of IR systems. So here's the comparison between IR and the DBMS. Some DBMS problems are not interesting or are not present in IR. For example, IR people don't care about updates, while DBMS have a lot of programs or code, a lot of lines of code to deal with updates. For airline transactions, airline reservation system, a lot of updates are done on a daily basis, right? They receive a lot of requests. They also try to reserve tickets, reserve on which airplane. So these are all updates. You have to tap in this data into the reservation database. Transaction management, that's a very important subject in DBMS. In DBMS, you're dealing with transactions. Transactions update DBMS, and you have to make sure that the transactions are serializable. So you have to develop some locking mechanisms or some concurrence control mechanisms to govern the execution of transactions. Okay, DBMS also deal with complex objects. Many DBMS deal with computer-aided design, KCAM, computer-aided manufacturing data objects, such as a house. For each house, you have parts. For the parts, you have materials. These are complex objects. And how to store this complex object in a DBMS, and how to retrieve data from the DBMS. So this computer-aided design, KCAM objects are particularly suitable for object-oriented databases, because object-oriented databases model objects using types and classes and so on, so that you can model these computer-aided design objects in object-oriented database systems. And these are issues that are most relevant to DBMS, while these issues are nothing to do with IR research. IR research doesn't care about updates. They always assume that you have a database there already, and you want to retrieve data. You see my point? You want to query the data, and then the data is presented to you. Okay, so right now, if you look at the Google search engine, that basically is a compromise or a combination of DBMS and the IR in the following sense. On the top, you see the IR interface. On the bottom, they use DBMS to maintain the data, or to, the search engine, the query optimizer for DBMS to process the underlying data. And then on the top, they give the data through IR algorithms to present the data in terms of ranking them and so on. So that's the combination of DBMS and IR. So IR people don't care updates, transaction management, and so on, while IR people care some of the problems that are not addressed well in DBMS. For example, IR deal with unstructured documents. They can deal with keyword retrieval. They can deal with documents, while DBMS doesn't know how to. DBMS handles documents in an awkward way. Okay, how to store a document in a DBMS? That's a problem. What they do is they still divide this whole document into several attributes and put this whole document as a tuple in a DBMS, or as several tuples in a DBMS. IR people care approximate retrieval and rank search results, while DBMS asks users to provide a query in an exact way using SQL statements. And then DBMS just does exact retrieval, meaning that you specify John and I just get a John returned to you. If John doesn't exist in DBMS, I'm saying sorry, John doesn't exist. IR can do slightly different. You present John, you say I'm interested in John. If a database, if in the repository, John doesn't exist, but the Jason exists, and Jason and John are relatives, then IR say, how about Jason? Do you want Jason? Something like that. IR can give you some solutions that approximate your query, although they don't exactly match. You provide a query to an IR system. You say, I'm interested in documents containing car. You are interested in car information. IR search engine looks for the database. Well, the database is not DBMS, just a collection of documents. And then they say, well, we don't have documents contain car, but we have documents contain vehicle. So they present these documents to the user. Will this be satisfied with you? That's how IR can do. But DBMS doesn't do that. You specify car. I look at the relational table. If there's no car, no attribute has car value, then I tell you no solution is found, even though a vehicle is there. A vehicle is similar to car in many senses, right? So IR people can do approximate retrieval, can rank the search results based on relevance to the query, while DBMS doesn't do this at all. And DBMS search language is very strict. You have to follow SQL or syntax, while IR query language is very flexible. You can just type in some keywords connected by or and. So these are main differences. Any question about this? And later on, when we talk about text mining, you can see the difference between text mining and the text retrieval, and we will address those issues at that time. So there are subtle differences between DBMS, IR, and the mining, KDD, and there are also similarity between them. Okay, last time I already told you about one main difference between data mining and the retrieval. Data mining always follows the paradigm: generate and verify. While DBMS is to do the search and the match, right? You want to find a John, so I use B-tree. I can find a tuple that has John as a name, and then present to you. That's DBMS. You want to find a car, IR can find the vehicles using some very fancy indexing techniques and present to you. This basically is like a search mechanism, search engine. On the other hand, KDD doesn't do this. KDD just generate patterns inside the repository, and for each candidate pattern, it verifies whether this is an interesting pattern or not, and present to the user. So it does something more than search. It generates and tests. Okay, that's KDD process. Any question about these subjects? There are two most important concepts you have to be familiar with. or two most important terminologies, terms you have to be familiar with when you are in IR. One is called precision, the other is called recall. What is precision? Precision tells you how precise your search is. Okay, use Google search engine, for example. You type in a keyword, and there are 10 search results returned. These are search results. So what is the precision here? Okay, here is the example of a precision. Suppose in the whole World Wide Web, or in the whole digital library, or in the whole repository, when you submit this query, there are 10 documents that are relevant to your query. Okay? Now suppose you try the Google search engine. Among the 10 documents, Google finds 8 documents and return to you. And then Google finds 8 of them, so 2 of them are missed. For that case, out of 10, Google finds 8 and missed 2. So the recall for this search is 80%. The recall basically is a percentage of documents that are relevant to the query. In my example, 10. There are 10 documents that are relevant to a query. And out of the 10 documents, how many are in fact retrieved? Google returns you 8. So out of the 10 documents in the whole library, Google finds 8 documents and present to you. And Google missed 2 of them. So the recall for this search is 80%, meaning that I found 80% of the relevant documents. Is that clear about recall? Suppose for this particular query, there are 100 documents in a repository or in the library that are relevant to this query. Suppose the search engine, whatever search engine you are using, can find 95 of them and miss 5 of them, 5 of these relevant documents. For that case, the recall for this is 95%. That is 0.95. Meaning that out of 100 relevant documents, 95 are retrieved. So the search engine can get 95 relevant documents, miss 5 documents, 5 relevant documents. Is that clear about the meaning of the recall? So intuitively, look at totally how many are relevant to this query, and look at how many are retrieved. Suppose 100 are relevant to this query, 85 are retrieved, 15 are missed. Then recall is 85 divided by 100. That's 85%. Any question about recall? Precision. What is precision? When the search engine gives you results, the search engine, for example, gives you 100 results with respect to this query. Only 90 of them are relevant. 10 of them are nothing to do with the query. So in other words, this is not 100% precise. There are 10 results that are irrelevant to the query. So the precision, what is the precision for this search? The precision then is 90, which are relevant to a query, divided by 100, which is the total number of documents retrieved. So the precision is 90%. 10 documents are nothing to do with this, and they are not included when calculating the precision. So, in other words, now you type in the Google search, you use the Google search engine, you type in a keyword, kindergarten, for example. You see a lot of search results ranked based on their relevance to kindergarten. You look at each page in turn, these are relevant, these are relevant. Perhaps out of the 100 returned search results, 10 of them are nothing to do with kindergarten, and we don't know why they are retrieved, by the way. They are just returned to you. For that case, the precision for this particular search or for this search engine is 90%. 90 out of 100 returned are relevant, so the precision is 90%. 10 are irrelevant to this query, or 10 documents are nothing to do with this query, so they are excluded from the precision calculation. Is that clear to you about recall and the precision? Any question? So in general, when you develop a search engine or when you are using a search engine, you would like your search engine to have high recall and high precision. The most ideal situation is that recall is 100%, meaning that if there are 1,000 documents in the library that are relevant to my query, all of them should be retrieved. Everybody should be in. So the recall is 100%. Precision is 100%. Why? What is that? That means For all the documents retrieved from this search engine, all of them are relevant to a query. Nothing is garbage. Everything is relevant to this query. That's precision. That means the precision is 100%. Did you find any search engine that has the precision 100% so far? Did you find one? I haven't yet. Google perhaps is the best one. Many search engines, when I type in keyword, that search engine gives me search results which are nothing to do with what I'm asking for. I don't know why those results are returned. So the precision is very low. Okay, in the worst case, suppose I submit a query, and suppose the precision is 0%, meaning that among all the search results, none of them is relevant to my query. And that's a very poor search engine for that case because it's so imprecise. Nothing relevant is returned. Everything returned is irrelevant. Is that clear about the recall and precision? Also, you want to have a high recall search engine. That is, if there are so many things that are relevant to my query, all of them should be gathered and should be presented to me. You understand? A high recall. For low recall search engine, if there are so many things there, while this search engine can only get 2 or 3 of them, then that's a low recall search engine because it cannot get these relevant search results. It cannot get many of these search results. Any question about recall and precision, about the definitions? I use examples to illustrate this concept, but the definition is given here. Okay? Precision is calculated by this formula. In the denominator, this is the total number of retrieved documents. For example, 100 documents are retrieved and are presented to the user. Out of the 100, how many are relevant? 80 are relevant. So the numerator is 80. 80 divided by 100, the precision is 80%. That means that 20 of the retrieved documents are nothing to do with my query. And I don't know why they are returned. The search engine must have some problems, and we have to improve the search engine. Recall, the denominator is the total number of relevant documents in the library. For example, there are 1,000 documents that are relevant to this query. And how many are retrieved by your search engine? Out of the 1,000, for example, 900 are retrieved by your search engine. For that case, the recall of your search engine is 900 divided by 1,000, which is 90%. It's a pretty high recall search engine. Okay? You don't want to have a search engine that has 0 recall, meaning that every time when you're typing a query, and suppose there are a lot of documents relevant to the query, unfortunately, none of them can be retrieved. So the recall is 0. It just cannot gather anything relevant to the query. And that's a very poor search engine. Is that clear to you about recall and precision? And these two are the most important measures when we talk about our system. Okay? We want to have a high recall and high precision our system in general. Now, most of these search engines are based on keyword-based retrieval. That is, a document is represented by a string which can be identified by a set of keywords. Okay, for example, we represent a document by 100 keywords. Okay, we can predefine which keywords are interesting, which keywords are not. Okay, so then we look at this document. If this document has this keyword, then we put the corresponding position 1. Otherwise, we put 0. So we can represent a document by a 1-0 vector, right? Does this keyword in this document exist in the document or not? Now, then queries may use expression of keywords. For example, I want to find a car and a repair shop. I want to find tea or coffee, DBMS, but not Oracle. You all know, you are all familiar with these keyword types of queries. Okay. So one difficulty for the keyword-based retrieval model is that it cannot handle synonymy and polysemy very well. What is synonymy? A keyword T does not appear anywhere in the document even though the document is closely related to P. For example, suppose my query is knowledge discovery. So presumably, if this document is describing something about data mining, that document should be presented should return to the user, right? But unfortunately, if you use a keyword-based system, you submit the knowledge discovery. And knowledge discovery doesn't match the data mining precisely, right? They don't match. Knowledge discovery, data mining, they spell very differently. Then for that case, the keyword-based system cannot retrieve that document, even though they are relevant. So the keyword-based system has difficulties in dealing with synonyms. It also has difficulties in dealing with polysemy. The same keyword may mean different things in different contexts. Mining association rules is different from mining minerals, which is different from mining classification rules. So for the same word mining, it means different things in different subjects and different domains. Okay? And keyword-based system cannot handle this well because keyword-based systems use exact match, string matching to do the retrieval. You have knowledge discovery, the document has data mining, they don't exactly match. So it cannot retrieve that document. And therefore, you can see that the recall will be very low because it meets a lot of relevant documents. Okay? So most R people prefer to similarity-based retrieval. We find a similar documents based on a set of common keywords. Okay? For example, if this document has these 5 keywords, that document has exactly the same 5 keywords. This document talks about knowledge. This document also talks about knowledge. So knowledge is shared by both documents. Knowledge occurs in both documents. This document talks about mining. That document also talks about mining. Mining also appears in that document. Mining occurs in both documents. If they share a lot of such common keywords, then this document should be relevant in some sense, right? So our system should be able to retrieve these relevant documents and then rank these documents based on the degree of relevance to a query, okay? Or based on the relative frequency of the keywords and so on. So this similarity-based retrieval is one very common technique used by IR systems, okay? In doing this, in developing these systems, you have to develop a stop list. That is a set of words that are deemed irrelevant, even though they may appear frequently. And they should be filtered out first because you don't want to include them during the retrieval. They will perhaps cause a lot of confusions. And these words include articles, a, the, prepositions of, for, with, and so on. So this list of words should be eliminated during pre-processing of documents. And stop list may vary when document size varies, okay? Word stem. Several words are small syntactic variants of each other since they share a common word stem. For example, drug, drugs, drugged. And we have to identify these word stems, okay? And we also maintain a term frequency table in which we know that how many times this keyword appears in this document and how many times this keyword appears in that document and so on. Once we have this information, we are able to define the similarities between two documents. One way to define similarity between two documents is to look at how many common keywords they share together. As I said earlier, this document has a keyword knowledge. That document also has a keyword knowledge, and the knowledge appears frequently, and it is an important word. If they share these important words, and they share so many important keywords, then these two documents should be similar. That's one way to define the similarities between two documents. Another way, which is one of the most commonly used similarity measure, is to use cosine distance. You model documents as Euclidean vectors. Okay? For example, suppose we have a bunch of documents here, and we have predefined 100 keywords, which are most important keywords that could possibly appear in these documents. For example, suppose I'm reading data mining papers. So these keywords might include data, might include mining, might include knowledge, might include discovery, and so on and so on. Clustering might include classification. This is also another important keyword. So among these 100 or these 200 data mining papers, I predefine a set of keywords. And then for this document, I check to see whether this keyword appears in this document or not. look at this paper. Does this paper contain the keyword knowledge? If yes, then I put 1. Otherwise, I put 0. In this way, suppose this predefined set of keywords has 100 keywords. So each document can be represented as a 100-dimensional vector. Okay? And if this, look at the knowledge. Suppose knowledge is considered as the first keyword. Then look at the article. Does this article contain knowledge or not? If yes, then the first coordinate will be 1. Otherwise, the first coordinate will be 0. 1, 0 indicates whether that keyword is present or absent in the document or not. Similarly, if mining is a second keyword, then I look at the second position. 1, 0. 1 means this keyword appears in that document. 0 means that keyword doesn't appear in that document. So on and so on. So I can represent a document by a vector containing 1, 0 values. Is that clear to you? And this model is called a Boolean model. Okay, each coordinate has 1, 0 values. 1 means the corresponding keyword appears in this document. 0 means this corresponding keyword doesn't appear in that document. So I can represent that document by a vector of 1, 0 values, 100-dimensional vector. Then I use a cosine. Once you have vectors, you can calculate the cosine of these two vectors, right? You know how to calculate cosine of these two vectors. You take the inner product of these two vectors divided by the product of their length. Okay? I give you a very, very useful example to figure out this cosine similarity measure. Suppose you have two documents, and suppose each document is represented by a 2-dimensional vector, 1, 0. Suppose this document has mining but doesn't have knowledge, so that's 1, 0. This document on the other hand has knowledge but doesn't have mining, so this document has 0, 1. Okay? You take the cosine of these two. What's the distance between these two documents? What's the cosine value for 1, 0 and a 0, 1? This has mining but doesn't have knowledge. This has knowledge but doesn't have mining. 1, 0, 0, 1. So these two documents have the similarity, what? 0, right? You take the inner product, 1, 0, 0, 1. The inner product is 0. That's okay. On the other hand, suppose this document has 1, 0. This document also has 1, 0. That means they both have the same keyword, and for the other keyword, that keyword doesn't appear in both of them. Then their similarity, after you take the cosine value, is 1. They are precisely the same document in terms of Boolean vectors. Any question about this cosine model, cosine similarity values? For any two documents, you model them as for example, 1-dimensional vectors. And then to calculate their similarity, you use a cosine function. You know how to calculate the cosine function between two vectors in a Euclidean space. Okay? For two vectors that are orthogonal to each other, 1, 0, 0, 1, their cosine value is what? Is 0, meaning that they are completely different. Which is true, right? Look at the 1, 0, 0, 1 example. This has one keyword here, but 0, they have a completely different keywords. On the other hand, if they have 1, 0, 1, 0, that means they have the same keyword, and for the other keyword, that keyword is absent in both of them. So 1, 0, 1, 0, they overlap each other, and their cosine value is 1, meaning that they are precisely the same. That's how we model do the similarity retrieval. Latent semantic index, that's a very big research subject. They use a linear algebra technique called the singular value decomposition technique. I can only give you ideas, but I can give you reference pointers in the WebCT. Latent semantic index can handle similarity retrieval or concept type retrieval in the following sense. If you submit a query car, and if the document has a vehicle, then the latent semantic index can retrieve that document and present to you. What this does is the following. The assumption is that similar documents always occur together. So if a document is describing car, the information about car, the document also should have vehicle keyword appearing somewhere, okay? Because they are similar. Car, vehicle, they are similar in concepts. So if you look at the Boolean model, car, vehicle represent different keywords, okay? They represent different keywords. So if you use the Boolean model to represent this document, that document might have 1,000 dimensions. Because car occupies one dimension, vehicle also occupies another dimension. Okay? So each document is represented by a 1,000 dimension vector. what latent semantic index does is to use singular value decomposition technique to reduce this 1,000 dimensional vector to a 100 dimensional vector. So that is, I basically group this car, vehicle, and so on, these similar words into one category. And then I use one representative word to represent that category. So I represent 10 dimensions using one dimension only. Car, vehicle, sedan, and so on, they will be grouped into one dimension, and they will be just represented one by one representative word. Okay? So for each document, initially it is represented by 1,000 dimensional vector. After singular value decomposition, I can represent that 1,000 dimension by a 100 dimensional vector, in which one dimension basically represents the 10 original dimensions. Okay? The represented word, for example, vehicle, can represent car, vehicle, sedan, van, and so on in the original document. Is that clear? So we can do the singular value decomposition to do dimensional reduction. Now, later on, when you present a query in which you have a car or you have a vehicle, okay? Now, when I do the match, I match with these 100 dimensional vectors. So you have a car there, and the car will be matched with the representative word for this dimension. And then you have a car, suppose the representative word is vehicle, I consider that as a match. So I can return this document to you, even though the words are not precisely the same. One is car, one is vehicle, but through the latent semantic indexing, we are able to identify that document which is relevant and which can be returned to the user. That's a latent semantic index idea. Okay? But the key thing is not the whole idea. The key thing is how you decompose, how you use singular value decomposition technique to reduce this dimensionality. Okay? And I can give you a relevant paper to look at this. There are other retrieval techniques like inverted index techniques, signature files. Both of them are for the keyword-based retrieval, and therefore they both have deficiencies. What is an inverted index? You look at your book, you look at the index page, right? For each word there are a lot of page numbers, right? That tells you that in this page you can find this word, in that page you can find that word. So those page numbers serve as pointers to the corresponding pages. That index is called an inverted index, meaning that for each keyword, you have pointers pointing back to the documents that contain that keyword. Okay? And for some smart index structures, they organize the index as a B tree, so that instead of listing this index sequentially, you can organize them as a B tree, so that you can locate a particular keyword quickly, and from that keyword you can find the pointers, and then find the corresponding documents containing, by following those pointers, you can find corresponding documents containing that keyword. Signature file is another retrieval technique for keyword-based retrieval. What this does is that we associate a signature with each document. So each document is represented by a signature. Okay? A signature could be a number, could be something else. And then a signature is a representation of an ordered list of terms that describe the document. Okay, and then when we do the retrieval, we can do the signature matching. So you do the integer matching, you can find the documents that contain a particular keyword. Okay, so that's a signature file. So basically, this review tells us what AI systems can do, what AI systems cannot do, the difference between AI systems and DBMS systems. Furthermore, what are techniques used in AI systems? The AI systems use a Boolean model to model documents, and they use keyword-based retrieval, for example, using the inverted index to do the retrieval. Keyword-based retrieval cannot find similar objects, similar documents. So they further use this the so-called similarity retrieval or latent semantic index to find the relevant documents, so that even a document doesn't contain precisely the keyword in the query, you can find the similar documents or relevant documents. You still can present those documents to the user. So this basically summarizes the AI research that is relevant to data mining. In the next subject, part 2, we will focus on text mining and see what kind of information will be discovered from text or from the semi-structured documents. This basically concludes this review of the AI systems, and I will basically stop here.